So, hello everyone. Myself R.D. Preshil. I teach everything related to psychology on skyrocket.com. Visit the website in your free time. And in today's video, we are going to learn about all the statistical operations which are possible in psychology. See, most of the students during undergraduation or master's stage, they don't know what is possible with statistics within psychological research. So, they are unable to frame different hypotheses using different statistical operations. Usually, whenever you want to frame certain hypothesis which to test for your project or for your paper, research paper or something, you need to have an idea of basic research methodology and statistical operations. Only then you can design a testable hypothesis which is novel enough and which can be tested. Okay. So in today's video, we are going to have a very broad idea of what are all the statistical operations which are possible within psychological research. First one, if you would like to test for differences between two groups or conditions, let us learn every statistical operation with an example. Okay. See, let us say this is your hypothesis. There will be a significant difference between academic self-efficacy between different caste groups. Okay. You're looking for differences between different caste groups and your dependent variable is academic self-efficacy, and you chose only two caste groups, or you chose gender, male or female or something. Okay. In group 1 there are different people, in group 2 there are different people. This is independent sample design. Okay. Independent design. Now what you will do is you will administer academic self-efficacy questionnaire to both groups at once and you will compare their means later. In this case, what is the possible, what is the appropriate statistical test to use? It is unrelated t-test, because see, in group 1 there are different people, in group 2 there are different people. Okay. And then there are other possible hypotheses with for this same statistical operations. See, let us say you want to see the difference between depression levels among male and female. Okay. That is also one of the possible hypothesis with this particular test. And you want to see the difference between IQ levels among science college students and arts college students. Okay. So all of these hypotheses are possible with this particular statistical operation. Every statistical operations which we are going to learn from now are very much can be easily performed on a software called IBM SPSS. You might have already heard about that, or if you are reading some research papers, you might have came across authors mentioning that we have used SPSS this particular version to perform this particular operation, and so. And when the operations go to a little bit complex, then we will use high-end softwares like MOS. MOS is nothing but one of the features of SPSS, and we will use R programming and all. Okay, I will tell you. Now the second possible test is, for suppose there is a significant difference between academic self-efficacy between different priming conditions. Let us say you want to test whether reminding someone of their caste identity will increase or whether it will decrease academic self-efficacy. So what you will do is, today you will administer an academic self-efficacy questionnaire to control condition, which means you will not remind them of their caste identity and you will not tell them that this particular study is related to caste. You will administer academic self-efficacy questionnaire, and after certain period you will administer the same questionnaire but after priming. Okay. After a 1 week or 14 days or so, you will tell them there is another study which is caste based study, and you will remind them of particular caste based stereotypes, and you want to see whether reminding them will significantly increase or decrease their academic self-efficacy. In these cases we are using repeated measures. Okay. See, in control condition also there are same people, in experimental condition also there are same people. We are repeating the same measure on the same sample. In this case, what will we use is repeated measures t-test. And there are some other possible hypotheses. For suppose, see, you want to check whether depression levels among individuals changes before and after a particular therapy. What you will do, you will give them a back depression inventory or any depression questionnaire to measure their depression levels before going to therapy. After two therapy sessions, or maybe after a 1 month of period of therapy, you will administer the same questionnaire again, and you will see, you want to see whether the therapy significantly changed their depression levels. So in these cases, you will use repeated measures t-test. Difference between loneliness feeling in individuals during holidays versus during college. All of these are possible with repeated measures t-test. If you would like to know this hypothesis, please pause the video and check them. Okay. Then there are, for suppose, yeah, this is a little bit interesting. I will see. I'll tell you. For suppose, your hypothesis is there is a significant difference between academic self-efficacy between different caste groups. Okay. So this is already we have tested. This is the same hypothesis from our unrelated t-test. Then what is this matched pairs design? For suppose, according to literature, income might confound the self-efficacy. Either it is general self-efficacy or in some cases academic self-efficacy also. Okay, this point is nothing but income, the family income or the individual's income will also affect their general self-efficacy and academic self-efficacy. And for suppose your groups, let us say your caste group 1 consisted of these people. Okay, first Ramu has 10,000 income, Ramesha has 10,000 income, and Raju has 70,000 income. And in group 2, Srinu has 30,000, Satish has 30,000, Soma has 30,000, and all, so on. See, if you carefully observe, in the group 1 average income is 30,000. Okay, 70, 80, 90,000 divided by 3 equal to 30,000. In group 2 also the average is 30,000. But here all of them do not have almost the equal income. Okay, but in group 2 almost all of them has the equal income. So what happens here is the income of this Ramu and Ramesh might affect negatively the academic self-efficacy in this group, whereas in this group all the three people, Srinu, Satish and Somu, might get the same academic self-efficacy scores. So in these cases what we will do is we will basically take care such that both the groups are similar in that particular confounding variable. For suppose, look, see here, you recruited participants such that in group 1 the average income here also is 30,000, and in group 2 here also it is the average income is 30,000, but the variance within this particular group is not much when compared to this case. Okay. Okay, so the variance in this group is not very much large than the variance in this group. See, there are only small differences. So in this case, we can conclude our results are more accurate. So whenever there is a confounding variable which might affect our dependent variable, we will usually use this matched pairs t-test. Okay, what are they? We'll see. For suppose you want to see whether there are difference between memory scores among males and females, and you designed and you recruited participants such that all the males are let us say they are topper students, and if you recruited all the female students who are dull or slow learners, then obviously you will obviously it will confound your study, right? Your memory scores will increase for males and it will decrease for females, or else vice versa. Then what we will do, you will administer an IQ test. For suppose, okay, you will administer the same IQ test for males and females, then you will take the participants such that same the both the male participants and female participants has the same IQ levels in both the groups. So similarly here, difference between loneliness feeling in introverts versus extroverts. For suppose you want to check for loneliness feeling in introverts or extroverts, what you will do? Possible confounding variable is whether they are in college or at home. For suppose you take all the introverts who are staying at home, and you take all the extroverts who are staying in college, obviously you will get a larger difference in the loneliness feeling of both these groups. Then what you will do, you will take only those only introverts or extroverts, either both of them should be staying at home or at college. So similarly there are many confounding variables depending upon your hypothesis, and you must take care that both the groups are similar. So in these cases we will use matched pairs t-test. Now, okay, all these three are parametric t-tests. Okay, whatever we discussed until now are called parametric t-tests, which are more powerful. The difference between parametric tests and non-parametric tests, I have explained in statistics bullet course. Please refer to that, which is a 30-minute video after this entire class. Okay. So what are the assumptions required to conduct these parametric t-tests, and what can we do if our assumptions fail to meet, or if our data set fail to meet these assumptions, or if our data sets violates these assumptions. Okay. First assumption is data must be at least interval level. Okay. The levels of measurement, you might have already know what are the different levels of measurements. Okay, uh, nominal, ordinal, interval, and ratio, and our data must be at least interval level. So whenever there are if you are using standardized questionnaires which are published or which are very well used in the literature, then you can safely treat your data as interval level. And if there are physical scales, for suppose height, weight, income, all of these are can be treated as interval levels. And the data set must form a normal distribution. Okay, usually whenever we would like to perform parametric tests, we will check for whether our data set is forming a normal distribution or not. The acceptable values. Okay, the acceptable values for skew is -2 to +2, and the acceptable values for kurtosis is -7 to +7. Usually we are more concerned about skew than kurtosis. In fact, in some papers it is also mentioned that the kurtosis value can be accepted until -10 to +10, and it is very rare. In some cases also skewness is accepted uh, from -3 to +3, and very rarely it is also accepted from -5 to +5. But if it is less than -2 to +2, it is very safe. Okay, then there is homogeneity of variance. See, this is nothing but here. See, here the variance is almost same. Okay, in group 2 and in here group 1 in this. Okay, what do we mean by variance is, see, the participants within a particular group do not differ much from each other. Okay, 5,000 difference is there here, 5,000 difference is there, and it is fine. But here, see, one participant has 70,000 income and the other participants has much lesser income. In this, the in-group variance is much larger than these three cases. So our data set must conform to homogeneity of variance. Usually this is checked only when our design is unrelated and the sizes of both the groups are very different. Otherwise, we should not say we need not check the for homogeneity of variance, but usually in most cases it will meet the homogeneity of variance when our data is related and both the groups are in same number. Okay, what if our t-tests, like what if our data set did not meet the assumptions of these parametric t-tests? Then we will use non-parametric t-tests. Okay, these are the alternatives which we can use instead of parametric t-tests. Mann-Whitney U, Wilcoxon t-test. Okay, not binomial sign test. It is not an alternative. It is an entirely different test, which I think is not very much useful, in psychological research. But please refer to it. Okay. Okay, so if you are testing for two conditions or groups and your data did not meet those assumptions, you can use Mann-Whitney U. And if it is if your design is matched pairs design, and then if your assumptions like if your data did not meet those assumptions, you can use Wilcoxon T signet rank T test. Now coming to unit 2, if you are testing for differences between more than two groups or conditions, see, until now we have checked only between two groups. Okay, difference between two groups, differences between two conditions, such that. But now we will see what we can do if we want to test for differences between more than two groups. Let us say, let us keep the dependent variable only one for now. Okay, which is academic self-efficacy. Now let us say there is just one independent variable but with multiple levels. Okay, see, previously I have shown only two caste groups. Now what I want to see is I want to check for the differences between three caste groups. Okay, And for suppose in another case there is a one independent variable with multiple levels. Oh, sorry. Yeah, more than one independent variable. See, if there are more than one independent variable, for suppose I want to see whether there is a difference between different caste groups, and I also want to see within those caste groups there is a difference between academic self-efficacy between different genders. See, the example is that I will give you a little bit of background. For suppose women face a particular kind of discrimination, and lower caste groups will face a particular kind of discrimination in society, and a researcher wants to see whether women from lower caste will sorry, whether women from lower caste groups will face double discrimination. Okay, they face discrimination being as a woman, they also face discrimination being as a lower caste woman. So whether such cases happen in real life, in in those cases also we can use this particular test. I will explain it. For suppose there are more than two independent variables also. For suppose there are three independent variables with multiple levels. I want to see within a difference between caste groups. I also want to see difference between genders, and I also want to see within educated caste groups or educated gender, or within uneducated caste groups and uneducated genders. So in all of these cases we will use something called ANOVA, analysis of variance. Okay, in here if it is a one independent variable, see in all of these cases we are using only one dependent variable. Okay, if there is only one independent variable, we will call it as one way ANOVA. If there are two, we will call it as two way ANOVA. If there are three independent variables, we can call it as three way ANOVA. The number of ANOVAs possible is many, like you can do a four way ANOVA, five way ANOVA, six way ANOVA, seven way ANOVA also. And if the levels, these represents levels within each variable. For suppose, see, caste has three groups within it, right? So and gender has two groups, then we will call it as 3 into 2. Okay, for suppose there are three caste groups, two gender groups, and there are two education groups, then we will call it as 3 into 2 into 2. In such a way, many different combinations are possible. 3 into 2 into 2, 2 into 2, 3 into 4 into 5 into 6. Many different uh, ANOVAs are possible, but the calculations and the analysis will get the interpretation of those, like the getting the results is very easy in SPSS. You will just select I want to perform so and so ANOVA, these are my independent variables and this is my dependent variable, but the interpretation of it will become complicated. Now let us say you have more than one dependent variable. Now okay, you have you want to see the differences between academic self-efficacy also, and you want to see the differences between generalized self-efficacy also. Then yes, similarly you might have one independent variable with multiple levels, you have more than one independent variable with multiple levels, and you have more three independent variables and multiple levels, and so on and so forth. In this case we will use something called MANOVA. Okay, MANOVA is nothing but it stands for multi-level analysis of variance. Okay, uh, when there are different, see, the these three caste groups within one independent variable are called as levels. Okay, and if there are two independent variables, in this case they are called as factors. Okay, multifactorial designs and multifactorial tests we call it as. Similarly, if it is a 3 into 2 test, we will use 3 into 2 MANOVA, 3 into 2 into 2 MANOVA and all. Okay, this is the basic difference between ANOVA and MANOVA. ANOVA can only be used when there is one dependent variable, irrespective of how many independent variables and how many levels within each independent variable are there. And similarly in MANOVA we will use multiple dependent variables, more than one DV. Any you can do it with two dependent variables, three dependent variables, four dependent variables, so on and so forth. Okay, now okay. Okay, so there is something called simple effect. There are three effects in ANOVA and MANOVA, like these multi-level analysis and factorial designs. There are three effects. First one is simple effect, second one is main effect, and the third one is interaction effect. Please leave the simple effect for now. I will explain two effects, mainly main effect and interaction effect. What is main effect? For suppose there is a caste group 1 and there is a caste group 2, and I have subjected both of them to 3 different conditions. Here, if you carefully observe, both group 1 and group 2 are getting similar results in all the conditions. Okay, in A, group 2 has a this particular result. In condition B, group 2 has this particular result, and the difference is not much between group 1 and group 2. And similarly, in third condition also, group 1 and group 2 scored similarly, which means here the main effect is for conditions. Okay, the larger effect is happening because of the conditions. And similarly, see here, for suppose in all the conditions, the both the groups are no. See, similarly, see here, there is a large difference between group 1 and group 2 in all the conditions. Okay, which means the groups actually differ than conditions, but in all the conditions they are almost both the group 1 and group 2 are scoring similarly. Okay, see, there is not much, y axis, no, there is not much difference between condition A, condition B and condition C within group 2. Similarly, there is not much difference between condition A and condition B and condition C in within group 1. Okay, these are almost horizontal lines. Okay, but there is a huge difference between group 1 and group 2, which means the main effect is here is happening because of the group. Then what is interaction? Interaction is something we discussed earlier. See, we discussed like, you know, uh, the women from lower caste group, women face discrimination because of their gender, and the women from lower caste group will also face discrimination because of their caste identity. So, or we can say social status. In such cases, double discrimination happens. So whether such interactions occur or not, how can we check? Let us say this group 1 is scoring in this way in 3 conditions. In group A, it is small, and in group B it is average, and in group C the group 1 scored higher. Whereas for group 2, the reverse actually happened. In condition A, it scored higher, much higher than group 1 when within condition A, and in group 2 both group 1 and group 2 scored similar in condition B, and in group C, I mean in condition C, the group 2 scored much lower than when compared to group 1. So what happened here? There is an interaction effect happening between conditions and groups. Okay, the analysis is much what we can say, the analysis is much informative only when we consider both the groups and the effects of conditions. Okay, so this is what interaction called. And for suppose if there is a possibility that both the interaction could also be there and there could also be main effect. What do I mean by that? For suppose, again, there is a gender, there is a caste groups. I want to see whether who will face more discrimination. There will be discrimination differences between different caste groups, and there will be discrimination differences between gender groups, and there will also be significant differences between you know gender and caste groups. For suppose women from lower caste groups might face more discrimination when compared to male from upper caste groups. Okay, so those kind of efforts will also happen, which means a particular data might also have both main effect and interaction effect. How? See, in this case, the group 2 and group 1 scored similarly in condition A. Okay, and in this case, the group 2 and group 1 scored somewhat different in condition B. And in this case, the group both the group 1 and group 2 scored very differently in condition C. But uh, both the group 2 and group 1 scored somewhat similar in within their groups, which means here there is a uh, main effect also, there is an interaction effect also. So if you did not understand from this lecture, please refer to only these 3 effects: simple effect, what is simple effect, main effect and interaction effect, from uh, some other videos, or please read some textbooks, try to read some textbooks and all, because the main agenda of this video is to introduce you with all the statistical operations which are possible within psychology, so that you can frame your own hypothesis, how to perform, how to understand, because there are many concepts within ANOVA and MANOVA, like what is between groups variance, what is with within group variance, and how do we calculate F ratio statistic. So I am not explaining all of this, because the main agenda of this video is to first introduce you to all the operations which are possible. Okay, imagine, you have rice. There are many items possible with rice. You can cook biryani, you can cook fried rice, you can cook tiger rice, which we call pulhora in Telugu, or you can cook white rice, you can do khichdi. You can do n number of things with rice. But how do we make them? We are not discussing in this video, just whatever the things that are possible. Okay, now within these ANOVA and MANOVA, there is a one variation which is called analysis of covariance. What is that? For suppose there is a variable which is not the interest of our study, but might affect the dependent variable. For suppose caste and gender are our main independent variables, and the income, the effects of income is not, you know, uh, the main interest of our study. In those cases, what we will do is, but according to literature, income is also a confounding variable which can affect the self-efficacy of individuals. In that cases, what we will do is we will control for income. Okay, see, there might be possibility that certain caste groups have higher average income than certain caste groups, or maybe certain gender group has higher average income than certain gender group. So in those cases, the the self-efficacy might differ not because of their caste or gender, but because of their income. So in those cases, what we'll do is we will control that particular confounding variable called as income in our case, and then we will see whether the groups will differ even after controlling for that particular confounding variable. That variable is nothing but called as covariate, and when we include such covariates in our study, we will call them as ANCOVA or MANCOVA, which is nothing but called analysis of covariance or multi-level analysis of covariance. So adding such covariates neutralizes that particular variable in a way. It assumes such that all the participants in the study has equal income. Okay, for suppose if you want to control for IQ, then what it will do is it will make your data such that all the participants has same IQ levels, or all the participants are come from same income backgrounds, and then it will check whether there are main effects or interaction effects with only our independent variables. So in the results will be much more informative and accurate. Okay, see, there is a significant difference between academic self-efficacy between different caste groups. A simple example: there is a group 1, group 2, and group 3. We will use one way ANOVA and all. There are repeated measures ANOVA is also there. Okay, we discussed about repeated measure. What is mean by repeated measures in the first when we were discussing about t-tests, right? Similarly, there are matched pairs ANOVA, there are repeated measures ANOVA, all of them. Please refer to them. Now, all of the tests which we have discussed until now has continuous variable. For suppose discrimination, we will employ a discrimination questionnaire, and the uh, dependent variable will be a number, a continuous variable. I hope you have an idea of what is a continuous variable, what is a categorical or nominal variable, what is a discrete variable, and all. If not, please pause the video and check them. Okay, what if our variables are not continuous variables and rather than they are categorical variables? Okay, for suppose let us start with an example. See, this is my hypothesis: more boys tend to accept than reject a blind date. Let us say go for a coffee with a stranger girl. Okay, in this case there is no there is no continuous variable. You will just ask 100 boys and 100 girls, would you go for, sorry, you will ask 100 boys, would you go for a coffee with a stranger girl? Then out of those 100 boys, how many of you accepted? 75 said yes, and 25 said no. See here, 75 people said yes. This is our dependent variable which has two categories, either whether they will say yes or no, and this is our independent variable male. In these cases, what we can do is we can perform chi-square analysis. In this case, we only have one row, right? Which means we have only one independent variable, right? So we will call it as one row chi-square. And for suppose you want to compare whether males will whether males will say more yes or girls will say more yes, then what we will do? See, in this case, my hypothesis is more boys tend to accept a blind date with a stranger girl when compared to girls. Here, I would like to compare it with girls, the results of boys with girls. You asked 100 boys and 100 girls, would you go for a coffee with a stranger boy or stranger girl? Then, out of 100 males, 75 said yes, 25 said no. And in females, out of 100 females, 40 said yes, 60 said no. So I want to compare both of these results, whether the result is, whether this difference is significant or not. In these cases, we will use chi-square, but in this case, since there are 2 rows and 2 columns, we will use 2 into 2 chi-square. Okay, so so when both of the, when both of our independent and dependent variables are categorical, we will use chi-square analysis. And uh, the table which we are looking at this is called frequency table. Okay, now there is a small variation of chi-square, which is a goodness of fit test. What this has only one dependent variable. Okay, for suppose, let us say this is your hypothesis: psychology students would prefer all the subdisciplines equally. There are number of subdisciplines, right? Clinical psychology, counseling psychology, quantitative research, qualitative research, and teaching. And you asked 500 psychology students which would they prefer. They preferred 100 people preferred clinical, 150 counseling, 75, 120, and 55. This is the data you got. Now what we will see is, you want to see whether this particular distribution fits the theoretical distribution or whether it departs significantly from the theoretical definition. That's it. You will not know whether, for suppose, the highest which is the highest preferred subdiscipline, counseling. Okay, more preferred people preferred 150. You will not know with this analysis whether the counseling has a significant significant interest from psychology students when compared to others. No, we will not know such results. What we will rather know is whether this whether this distribution that we got fits the actual theoretical distribution or the expected distribution. See that what is, if this hypothesis is true, psychology students would prefer all the subdisciplines equally. If that is true, what should actually happen? All the subdisciplines should get interest from 100 students, right? When you ask 500 students, but here it is departing. Whether whether this departure is significant, whether is this difference is significant or not, we will say with goodness of fit test, and we will use chi-square only. Okay, now when there are variables more than 2, okay, all of your independent and dependent variables are categorical here, and you want to see whether there are see, for suppose more boys tend to accept this is your hypothesis, tend to accept a blind date with a stranger girl when compared to girls. But whether they say yes or no depends on their relationship status also. Okay, this is your particular hypothesis. Now you want to see whether it is true or not. And here we will call this as multi-way frequency table. You will see in male how many of are within in a relationship and how many of them are single. You ask 100 relationship males, 100 single males, and 30. This is the distribution you got. Okay, there are more than, there are more than 2 variables here. There is a independent variable which is called gender, and there is also relationship status, which is another independent variable. In these cases, we will perform something called log linear analysis. Okay, all of these are performing these statistical operations are very much easy in SPSS. All you need to do is, you need not know if performing every statistical operations. First frame your hypothesis, and you must know which statistical operation you must perform in order to get your results. And you can go to anywhere, you can go to chat gpt, or you can go to DeepSeek, or you can just go into Google. You can go anywhere and you can just type, okay, this is what I would like to perform, and what are the assumptions that my data must meet, and give me the step-by-step tutorial to perform this particular uh, statistical operation. Then it will give the detailed steps for assumptions also. Okay, I have just discussed about parametric t-test assumptions, right? And I will again discuss about correlation assumptions. But okay, similarly, I did not explain the assumptions for ANOVA and MANOVA, and I will not explain the assumptions for regression because they are much more complex. Okay, so in those cases, what you will do, you need not remember every assumptions that are required for your data set for every statistical operations. All you need to do is, you have a particular hypothesis, you need to perform a particular statistical test. You will go into the Google, you will type what are the assumptions that my data must meet, and give me the step-by-step tutorial to perform it in SPSS. Then you're good to go. Now, now coming to correlation. Okay, I hope you already know what correlation is. You will test for strength of association and direction between two variables. You want to see correlation between two continuous variables. The reason I have specifically mentioned continuous variables is we will also see for nominal and nominal variables also. See whether they, you want to check for whether there is a significant correlation between depression score on BDI, back depression inventory, and social media usage. There is no such SM usage scale. I have just created, like, as an example I have mentioned it, or there might be very many social media usage scales on in literature. Okay, let us say these are the scores. Participant number 1, 2, 3, or suppose has scored like this. Continuous variables will look like something like this, and you want to see whether there is a significant correlation exists between these two variables. What you will do? You will administer both the questionnaires on those participants, and you will check for, and the statistical test which is needed for to check this particular correlation is Pearson R. Okay, this is a parametric correlation. This is the only parametric correlation that there is when it meets certain assumptions. Okay, what are the assumptions for parametric correlation? Again, the data must be at least interval level, data set must form a normal distribution, there should be a linearity in scatter plot. What is scatter plot and what is linearity, I will explain. Okay. Okay, see, you already know positive correlations and negative correlations, right? See this example. When this variable is increasing on x-axis, this variable is also increasing, which is nothing but called positive correlation, which means the correlation is linear here. And similarly here it is negative. When this correlation is increasing, this correlation is decreasing. This is nothing but called negative correlation. You see the dots here, every dot represents a participants in this scatter plot. Okay, and this particular scatter plot must represent some linearity. It could be either this, or it could be either this, or it could be either this, but it should not be like this horizontal. No, if it is horizontal means there is no correlation. And sometimes for suppose he see, do you think that there is no correlation here just because the line the scatter plot is not linear? No, these are called as non-linear correlations. Okay, we will not use at this level. There are cubic correlations, there are exponential correlations, there are logarithmic correlations. I can explain with each with an example. For suppose this is nothing but called Yerkes-Dodson law. uh, when stress, yeah, there is a correlation between stress and effort. When the initial stress is somewhat minimal, the effort will keep on increasing up to certain level only. But the stress is very much more. If the stress is too much, then the effort you will keep for that particular task will decrease. This is Yerkes-Dodson law, which has quadratic correlation. And there are exponential correlations, logarithmic. We can actually see in exponential correlation. For suppose you are going to gym, in the initial stages there might not be, for suppose your these are days, and this is the change or weight loss. Okay, in initial days you might not see much change in your weight or within your body, but after you will hit a certain point after which your weight loss will keep on increasing exponentially, and this is logarithmic, which means the reverse of exponential. Actually, in the initial stages it will increase rapidly, but after some time uh, you know it will settle down. uh, Let us say, in love marriages or something, in the initial stages the love is too much, and after certain stage it will get you know normal or something. Let us say cubic correlations are for arranged marriage or something. In initial stages the love is too much and it will settle down. And for suppose there is something, okay, in any marriage there is a situation in which one of them has fallen sick, and the other person showed responsibility or something, then the love might actually increase for the other person. So all of these correlations are possible. I have given a very bad examples, but just know all of these correlations, these non-linear correlations exist. But in order to perform Pearson R, your correlation must be shown as linear. Okay, if it is horizontal there is no correlation, and if if your scatter plot shows any shape as such, I have shown now, they are non-linear correlations. And there is something called homoscedasticity. The names are name sounds very sophisticated and complex, but the concept behind it is very easy. See, excuse me, your correlations, I'm sorry, your scatter plot must look something like this. Okay, if you draw two lines with such that within which your entire participants would fit, the lines must be parallel enough, which means for every x value the variation in y should be same. Okay, see here the variation is same, and here also the variation is same, here also the variation is same, here also the variation is same. But for suppose look at this, here the variation is this much, but here for this x value the variation in y is this much, for this particular x value the variation in y is this much, and the variation is keeping on increasing. Okay, even if the lines are like this, it does not meet our assumption of homoscedasticity. If the diagram looks like this, it meets the assumption of homoscedasticity, and if it looks something like this, it uh, it has something called heteroscedasticity. Okay, if our data set did not meet these particular assumptions, then what we can do? We can perform non-parametric correlation, which is nothing but called Spearman's rho. Okay, now if you want to see correlation between two truly dichotomous variables, what do you mean by dichotomous? What do you mean by truly dichotomous? See, suppose a variable which has only two categories is nothing but called a dichotomous variable, male or female, heads or tails, yes or no, employed or unemployed. Actually, we can use many genders here, but you know, for example, okay, all of these are called dichotomous variables, and you want to see whether there will be a correlation between gender and saying yes or no to a blind date. Why these are required? Why not why not we use chi-square? Okay, just like in the in the previous examples we have used chi-square to see whether there are significant difference between male and female, in whether they would say yes or no to a blind date, right? Why? Because to be able to use regression and to be able to do much more complex analysis, so to make those analysis possible, we will use correlations. How? We will see when we get to know the regression. Okay, in these cases, what statistical operations we will use? We will use Phi-Coefficient statistical test. Okay, again, all of these are possible on SPSS. For example, you want to see correlation between one truly dichotomous variable and the other at interval level. Let us say, what is your truly dichotomous variable here? Females and males. And what is your interval level variable here? There is a high depression levels among females than males. This is your example. And your scores for each participant, each male participant, and for each female participant, there will be certain BDI score, right? And let that be a maximum score of 50. And the average of all the males participant and female participants are this. Okay, you conducted on a sample of 100, they scored 35 and they scored 52, and you want to check the correlation between these. What will you use? You will calculate something called point biserial correlation coefficient. Okay, it is denoted by r suffix pb. Okay, for suppose you want to see the correlation between one artificially dichotomous variable and other at interval level. What do you mean by truly dichotomous and artificial dichotomous? Here, truly dichotomous means they exist as it is in real life. Okay, yes or no, heads or tails, they exist as it is. But here what we will do is we will decrease these categories from an interval level data. Okay, for suppose you want to see whether IQ levels correlate with depression scores. Okay, you can directly do with IQ levels and depression scores. You can do the Pearson or such, or else you can divide first the higher IQ level people and lower IQ level people. Okay, see 150, 140, 130, 120, 110. These are reduced from interval level to a categorical level, which is nothing but called artificial dichotomous variables. Okay, when there are only two categories, high IQ people and low IQ people. Now you want to see whether their BD depression scores has significant correlation with high IQ or low IQ. Then we will use something called biserial correlation coefficient, which is denoted by R and R suffix B. Got it? Coming to regression, what is regression? You know, it is an extension of correlation actually, but regressions are very powerful. Regression is very powerful statistical operation. There are various types of regressions, and regression is actually the basic for much complex analysis like conditional process analysis, structural equation modeling, moderated mediation, mediated moderation, and all. So we will see, when we want to know the strength of prediction of one variable from another correlated variable or from several correlated variables. Let us say you have one criterion or outcome variable, and you want to see what are all the variables which can successfully predict this particular outcome variable. Best example is, for suppose, um, what do we call pelli choopulu in English? Mm. For suppose there is a matchmaking in marriages and all. No, you want to see what are all the variables which can successfully predict whether that particular bride or bridegroom will say yes or no to the marriage. In here, that bride or bridegroom saying yes or no is dependent variable, and all the other predictors like financial status, physical attractiveness, maybe caste of parents educational status, everything will be independent criterion variables. So in other maybe other example, what are the variables that can successfully predict job performance? Example, salary might predict successfully job performance, job satisfaction, years of employment, and all will, maybe they can successfully predict job performance. And in regression we can also tell which of these predictors are successful than others. Okay, see, we want to know the strength of prediction of one variable from another correlated variable or from several correlated variables. For suppose you want to see your outcome variable is job performance. Which of the variables will predict successfully this particular job performance, or how much successfully each variable can predict? And you have three variables, right? Salary, job satisfaction, and years of employment. Each will have a particular amount of correlation, right? See, salary might have a positive correlation with job performance. Higher the salary, maybe the better the job performance will be. Job satisfaction might also will have the positive correlation. Okay, each predictor variable has certain correlation with criterion variable individually. These are the basics of regression. And years of employment, maybe it is negative. Okay, more the years a person spends in a job, he might get bored. Okay, so maybe it has weak negative correlation with job performance. Similarly, so it will look something like this. Okay, this is nothing but called the variation within job performance that is explained by salary. Okay, this part. And what is this part? This is the variation in job performance that is explained by years of employment. And what is this part? The variation within job performance that is being explained by job satisfaction. What is this remaining part? The variation within job performance which is unexplained by all these three variables, which might be explained by other variables. Okay, there might be other variables which are also deciding, which can also decide job performance, whether they are working in hybrid or office or online mode, or whether they are male or female, whether the position or designation of that particular job. All of this might can also explain job performance. Okay, so no matter how many variables you add to it, there will always be certain variance which can which is left unexplained. Okay, each predictive variable has certain correlation with the criterion variable individually. This is the diagram for it. Now see, there are correlation between not just predictors and criterion variable, but also in between predictors also. Okay, see, for example, not just salary and job performance will have a correlation. Salary and job satisfaction might have also have certain correlation, right? Let us say that be 0.6, and job satisfaction and years of employment will also have certain correlation with each other, 0.7. Okay, predictors will also have correlation in between. Okay, see, and the actual diagrams will look like this. Okay, see, the shaded, the common part between the years of employment salary is nothing but called correlation between salary and years of employment. And the portion which is overlapped by these circles in the white region, in job performance region, is nothing but called the variance explained by all of these three variables. Okay, the actual diagrams will look like, you know, they are much complex and look like this. Okay, you want to predict exam grades. What are the successful predictors that can predict your exam grades? There might be it might be numeracy, it might be motivation, teaching satisfaction, attendance, teacher liking. All of these can, you know, predict exam grades successfully. Or else when you do regression, some of these might not be significant, you know, significant predictors, which means some of these might not be effective predictors. Okay, let us say weather during exams might not be a significant predictor. Okay, so these are the basics of regression. Okay, and there are certain what do you call, notations or denotation. There are certain coefficients which you need to know. Please don't worry about B weight and beta right now, but I will explain. The main things you need to know right now is R and R square. R is nothing but called combined correlation between all predictors and criterion variable. Please wait, I'll explain with an example. And R square is proportion of variance explained in criterion variable by all predictors together. See, let us say you conducted regression on this example. Okay, you conducted regression on this example. Now, there is teaching satisfaction, there is teacher likingness, there is attendance, there is motivation, and there is numeracy, and how each predictor will predict your exam grades. See, this B value is there now. This B weight is nothing but for each unit increase in teaching satisfaction, there are 5.102 units of increase in exam grades in our criterion variable. Okay, and look at this. For each unit increase in attendance, there will be 1.252 increase in units in exam grade. Similarly, motivation, similarly, numeracy. But if we see teacher likingness, there is actually decrease in for each unit in teacher likingness, there is actually decrease in exam grades in our criterion variable. Sometimes it doesn't feel right? Okay, if you like the teacher, you actually it should actually predict our exam grades positively. But due to the you know, that our data might not be that much have that much quality, or sometimes these kind of mistakes happen, and it turns out some predictors are less significant than others. See, here there are significance values. Okay, teaching satisfaction is significant, and motivation is also significant, and numeracy is also significant, but these two predictors are not significant. See, just like we assumed, teacher likingness is predicting negatively, which doesn't fit right with theory, so that's why it turned out to be not significant. Do not use the word insignificant. Okay, and the reason I have added this is because he is Anupam Kher from the scene of Kartikeya 2, in which he gives elevation to Lord Sri Krishna, in which he says he is everything and he is everywhere. So in previous classes, I have actually told that this significance will not leave any statistical test. It will come everywhere, whether you're doing an T test, whether you're doing correlations, whether you're doing log linear analysis, whether it is a conditional process analysis, whether it is regression, whether it is structural equation modeling. So just like you know, he says about Lord Sri Krishna, significance values are everywhere. So that's why I added him. Okay, so this is nothing but called B weight, and the standardized form of B weight is nothing but called beta. They are expressed in standard deviations. Okay, which means for every one standard deviation of teacher teaching satisfaction, there are 0.485 standard deviations increase in our criterion variable, which is nothing but called exam grade. Similarly, all of these, out of all these, only there are three significant predictors: teaching satisfaction, motivation, and numeracy. Okay, now let us see how much variance. Okay, we see in the Venn diagram, right? We seen this diagram, right? This much variance is being explained by all these variables. Okay, for suppose this one. Okay, all of these circles are overlapping with this particular exam grade diagram, right? So how much variance is actually this first one? R is nothing but combined correlation between all predictors and criterion variable. Okay, what is that combined correlation? For suppose, you know, salary has correlation of 0.3, job satisfaction has correlation of 0.4, years of employment has 0.2. When we combine all of these, and I don't mean addition, when you combine all of this, you might get something called 0.6 or 0.7 or something. That is nothing but called R. Okay, but this is not the most useful statistic in regression. The most useful statistic regression is actually R square. When you multiply 0.75 into 0.751, you will actually get 0.56400 0.56, you will get some value. Okay. So this is nothing but called variance 50, which means 56.5% of variance is actually being explained by all the predictors combined. How much? 56.54. But still this is not much more useful when you are using multiple regression, because when you are using multiple predictors, the actual variance explained by these predictors is sometimes overestimated, and that is why we will use adjusted R square, which is nothing but called 0.518, which means actual case in actually 51.8% of variance within exam grades is explained by all the predictors that we have mentioned. Okay. So that is what regression is all about. That is how our regression is useful. Okay. You want to see how much, which is nothing but called, see, you want to see whether physical attraction predicts love, and let us our love is let us say our criterion variable, and we have one predictor, only physical attraction. Okay. Let this is very bad example, but let us assume love as a continuous variable. Okay. You have a love questionnaire, and it gives you interval level continuous data. Okay. You can score it. Then what is the correlation between physical attraction and love? Let us say it is 0.3 in simple linear regression. See, this is nothing but called simple linear regression when you have just one criterion variable and just one predictor variable. Here the R value, the combined correlation value, is nothing but called this single correlation value, because you do not have multiple correlations, right? You do not have multiple predictor variables. So equal to 0.3. Then what is R square? 0.3 into 0.3, which is nothing but called 0.09, which means 9% of variance of love, which means it is being explained by physical attraction, which means the amount of love depends 9% on physical attraction. Got it? Okay. Now, what if our criterion variable is categorical? See, possible predictors in arranged marriage decisions are physical attractiveness. In interpersonal attraction also, we might have studied these, right? Physical attractiveness, proximity, similarity, complementarity, gender, etc. And our criterion variable is yes or no, whether that bride or bridegroom will say yes or no to that particular match. Here obviously criterion variable has more than two. Wait. Okay, when it has just two categories, we will use binomial logistic regression, and usually it is called as just logistic regression. Okay, the short form for binomial logistic regression is just logistic regression. Whenever they mention logistic regression in research papers and all, you must know that it is just binomial, which means the criterion variable has only two categories: yes or no, heads or tails, employment or unemployment, pass or fail, and something. And if that criterion variable has more than two categories, for suppose, what are all the predictors that can successfully predict whether a student chooses Andhra University, Geetam University, or St. Joseph College for their postgraduate in psychology program? Then we will use statistical test called multinomial logistic regression. Okay. Do not use the term polynomial, because most of them remember the opposite of binomial as polynomial. Please don't remember it as polynomial regression, because polynomial regression is actually used in structural equation modeling and it has different use cases. Okay. Don't use this term. Use only multinomial logistic regression. Both are not same. They cannot be used interchangeably. And the assumptions for regression are much more complex. The required sample sizes for regressions are much more complex, because the regression is very powerful analysis in the psychological research, which is the basic. Okay, correlation is basic for regression, and the regression is the foundation, the roots for much more complex analysis, which we will see now. What is this mediation, moderation, and conditional process analysis? See, what is a mediating variable? A mediator explains why or how a relationship between two variables exists, acting as an intermediary. Intermediary means something called as broker in the causal sequence. Okay, with this there is a a critical concept you must understand here. Whenever you would like to use, okay, I'll explain it later. Please wait, please wait. What is a mediator? For suppose when the weather is hot, obviously the sales of soft drinks or cool drinks will increase. This is obvious, okay, isn't it? But how can increase in weather will impact these cool drink sales? In here, what is our independent variable? Weather. Okay, fine. What is our dependent variable? Soft drink sales. But in moderation, mediation, and CPA, we will actually call independent variable as antecedent variable and dependent variable as consequent variable. Remember those terms for now. But for simplicity, we will refer to them as IV and DV. Okay. So we will see how weather will affect cool drink sales. It is very unlikely that cool drink sales will affect weather, right? Okay. Now, how? Weather will increase thirst first in individuals. Then they will buy soft drinks. Okay. Isn't it logical? So here, since the weather first will cause an increase in thirst and then it will cause cool drink sales, is nothing but called, this variable is nothing but called mediator, and this is nothing but called a mediation model. Okay. Sometimes to analyze a particular variable as a mediator, you must provide a literature, you must provide evidence from literature to justify to use that particular variable as a mediator in your analysis. But how can you infer that this particular mediator, is the cause for an increase in independent dependent variable because of this independent variable? It is like a back and forth process. First you need literature to justify, then you will use analysis, and you will then add much more evidence to that particular mediator as a causation variable. Okay, it will become complex if I try to explain, but leave it for now. Then what is moderator? Okay, moderator usually determines when or under what conditions that particular relationship occurs. We will use the same weather and cool drinks example. See how thirst, increase in thirst will increase in cool drinks sale. Okay. For suppose, just look at this particular relation. Okay. Obviously, when there is increase in thirst, cool drink sales will increase. Okay. But how and when? For suppose price of cool drinks is very high. For suppose your country's government has more taxes on soft drinks. Then is there a chance that the cool drink sales will increase? Obviously no, because they will be costly and people will be hesitant to buy them. But if the price of cool drinks is very less, okay, then what happens? When there is an increase in thirst, obviously there will be more cool drink sales, which means here the price of cool drinks is moderating the effect of this particular mediator on this particular dependent variable, which is why this particular variable is called as moderator, represented by W or Z, which means when there is only just one moderator in your analysis, you will represent it by W, and when there is a second one, you will represent it by Z, and this is nothing but called a moderation model. Okay. So a moderator decides under what conditions or when a particular mediating effect will occur. So when there is thirst, obviously there will be cool drink sales only when the price of cool drinks is low or reasonable. If the cool drink sales, soft drinks are very high, okay, let us say 1,000 per liter or something, then obviously cool drink sales will not be much higher, which means it will moderate this particular causation effect. Now let us see much more complex. We'll bring in multiple moderators into this particular mediation model, and we will see uh, where exactly that placing that moderator is appropriate in this particular model. Okay, for suppose take price of cool drinks. Okay, there are various causations here. Weather will cause increase in thirst, obviously. Tell me if whether increase in thirst depends on the price of cool drinks. See, price of cool drinks will obviously affect this particular direction. Whether increase in thirst will lead to more cool drink sales depends on the price of cool drinks, obviously. But tell me the causation which weather is causing in increasing thirst, whether this effect is moderated by price of cool drinks? No, right? Whatever the price of cool drinks might be, an increase in the temperature in weather will definitely cause an increase in thirst. So the what is the position to place that particular moderator? This particular position. Okay, see, price of cool drinks is placed here. This model is nothing but called as moderated mediation. Now let us say an individual might stay either in home or outside during summer. Okay, now this particular moderator, whether it will which which direction, in which direction it will affect, whether it will affect this particular direction, we'll see. There is an increase in temperature in the weather and your thirst will be increased. Tell me if it depends on whether you stay at home or outside. Obviously in home you will feel much less heat, then the thirst will also decrease only, which means there will not be much increase in your thirst. And if you're staying outside, obviously it will affect your thirst. Okay, so this is affecting your, this is moderating this particular direction also. And tell me if it affects this particular direction also. Okay, there is a increase in thirst. Now whether you will purchase a particular cool drink sales or not will depend on whether you are staying inside home or whether you are staying outside. If you are staying inside home, you will make a lemonade or you will just drink cool water or something and done, and then you're done. But if you're staying outside, then you will obviously have a higher chance of purchasing cool drink sales. In these cases, there is possibility that this particular moderator will affect both of these directions. Okay, and when we combine both of those moderators into one particular model, this is nothing but called multiple moderated mediation. Okay, and that particular term is called conditional process analysis. CPA is nothing but called combined time for all moderated mediation and mediated moderation models. Okay, moderated mediation is very much useful, but mediated moderation is not very much useful according to Andrew Hayes. He is an author of Introduction to Mediation, Moderation and Conditional Process Analysis. He is also the creator of Process Macro, which is a plugin for SPSS through which we can perform these mediation analysis, moderation analysis and conditional process analysis through his Process Macro. And if you remember from previous classes, I have told you an example that your hypothesis must have a practical implication, in which one of the researcher called Hayes studied whether the college students, whether they will choose the first benches or last benches. And when he wanted to publish, he got rejected because his particular study did not have sufficient practical implication and all. So that study is done by none other than but him only. His name is Andrew F. Hayes. There is a book on mediation and moderation and CPA, so please refer to them. Okay, how many these kind of models are possible? A total of 93. A total of, as of today, according to his latest edition, according to the Process Macro, the version right now, a total of 93 models are possible, of which each diagram, each model is shown in his textbook. Please refer to it. And there are something called parallel mediations are there, serial mediations are there, in which parallel mediations are nothing but there might be two factors which can cause a particular dependent variable individually, and there might be serial mediation, which means one particular independent variable will affect a particular mediator first, and then particular mediator will affect another particular mediator, and then that particular mediator will affect the consequent dependent variable. So in these cases we will use serial mediation, and the combination of parallel and serial mediations are also possible. Okay, please refer to it. So conditional process analysis looks like something like this. Okay, all of these are coefficients which explains the strength or direction of that particular relationships or directions. Okay, whether they are significant or not. Okay, see here it is significant, significant. This is not significant, see. Okay, so this is how conditional process analysis is done. But in moderation, mediation and conditional process analysis, we can only do with one dependent variable only. What if you want to check for more dependent variables? All of these are possible only with one dependent variable. What if you want to analyze these operations on multiple dependent variables? You can do something called structural equation modeling. Okay, this can be performed with MOS, which is movement of structures, analysis of movement of structures. Okay, short form. This is it can be done in SPSS, and the diagrams will look more complex, and they look something like this. Okay, here there are three dependent variables, and all of these are mediators or moderators or something. Okay, see here, behavioral intention 1, intention 2, intention 3, all of these are three consequent variables. Okay, so here also there are multiple dependent variables, and uh, they'll become complex and more complex. Okay, so you can use structural equation modeling also. Okay, this is how, see, these many statistical operations are possible within psychology itself, and these conditional process analysis and all are mostly useful to infer causations. Okay, if a mediator turned out to be a significant, that particular mediation turned out to be a significant in that particular mediation model, we can infer causation actually. But you need literature, you need justification from literature to use that particular mediator as a sorry, that particular variable as a mediator, and again you can use that particular analysis to justify you using that particular variable as a mediator. Yeah, so okay, so they are a little bit complex initially, but knowing whatever possible with the statistics in psychology will help you design and frame your own hypothesis, at least in master's level. Okay, so this much understanding is very much required to frame your own hypothesis and to conduct your particular study. Let us say you have a hypothesis, you have something in my mind, and you don't know what to do. Then what you can do is you can just go to ChatGPT and you can say, this is my particular hypothesis and this is what I want to do. So okay, I deliberately did not explain something called say, single sample t-test. There is something called single sample t-test. Okay, for suppose you want to see whether there is you want to compare the IQ levels of those who takes PhD in quantum physics, because quantum mechanics is very much complex, right? So you want to see whether you want to see how much high the IQ of those particular people along with the standards. What are the standards? 100 is average, right? For IQ for general people. So when there are already standards of a target population, you can just use a single sample to check if this single sample differs significantly on a particular variable from the standard populations or that target population standards. Okay, so in those cases you can use something called single single sample designs. So you might have something hypothesis in mind, and you don't know what statistical test to perform, or you might not even know whether a particular statistical test exists to test your own hypothesis. Then what you can do is you can go to ChatGPT, you can give your particular statement or hypothesis, then you can ask them, okay, what are all the statistical tests that I can use to perform this particular test, or what is the best statistical test to perform or test this particular hypothesis. Then it will give you certain statistical operations, or if there is only one statistical operation, it will give you then you can see whether that statistical operation really fits for your to test your hypothesis. Then you can learn it from the chat gpt or from any AI itself. You can perform it, is as simple as that. But you need this understanding to frame this particular hypothesis first. Without knowing these particular statistical operations or methodology is possible, how can you frame your different hypothesis? Mostly you might be able to frame your hypothesis for correlations, or mostly simple regression. There are various regressions also. There is something called hierarchical regression also, which is nothing but multiple regression, but it is the perform no you will perform multiple regression within each stage, which is nothing but called hierarchical regression. Okay, so these many regressions, these many operations are possible within psychology, and knowing them will help to frame your own hypothesis. So I hope this video helped you. If you guys are having any doubt, you can comment down below, or you can contact me directly. Okay, I would love to help. There are many videos on my YouTube channel as well. There are different videos. There is something called statistics bullet course in my video. I'll in 30 minutes I will explain which test to use when, and the alternatives also there. Okay, I just use 2 diagrams to explain entire statistics. Please refer to that also. It is a, I believe it is a necessary and a very good add-on to this particular video. Thank you guys. Thank you so much for watching till the end. If it is helpful for you, please share it to some of your friends, like, share and subscribe and all. Okay. Goodbye.